Hello, we're going to start section 3.3 now. It's about maximum and minimum values. So over here, we're going to talk about the third application of derivatives. To be honest, one of the best applications of derivatives is the fact that it optimizes. Later on, I will describe optimization in a much better way. Wow, I will be giving more information about that. But before talking about optimizing, which is application in the real world, we're going to talk about applications mathematically. See, we are in most of our lives, we aim at finding the maximum and the minimum of a function, of anything in life. We want to use, for example, if we have a lot of land, we want to build on it the house with the maximum area and the best conditions. We want to have the biggest profit. If we are a company, we want to pay the least costs and have the biggest profits. So it's always our aim to either have the maximum of something that is good or the minimum of something that is not good. So we always aim at maximum and minimum, which we call extreme values. Now, what does it mean to have an absolute? There are two kinds of max and min values. There are what we call absolute max and min, and there are what we call local max and min. I want you to know that these two are different. If it's absolute, it doesn't mean it's local. If it's local, it doesn't mean it's absolute. One does not contradict the other. It might be absolute but not local. It might be absolute and local. See, yani they can happen together or not together. They do not contradict each other. They are two different definitions and they work in different ways. So that's why we do not assume that they are the same thing, and we do not assume that one leads to the other or vice versa. So let's first start with absolute max and min. What do we mean to have an absolute maximum? See, if we have a function f and we have a set S of real numbers that we are dealing with. So it might be the domain of the function, all the domain, or smaller than the domain, any set you pick and you define this function over it. So I might say I want f of x defined from 1 to 3 only. I don't want it defined on all real numbers. I want to define it only to take a piece of it from 1 to 3. So this is called then a set S, any set S you choose. If f of c, where c is in S, is greater than or equal to all f of x, where x is in S, makes sense. So if f of c is greater than or equal to all f of x for all x in S, so this f at c is greater than or equal to f of x for all x in S, we call f of c the absolute maximum value of f. Be very careful. I ask many students later on, they will say, for example, c is the absolute maximum. No, c, x equals c, is where the absolute value occurs. But the absolute value itself is the value of y. Now, what do you imagine an absolute minimum is? If f of c, another c, not the same c, another c. So those are theories, right? We're saying when do we define f of c to be a max and when do we define it to be a min? If f of c is smaller than or equal to all function values at x belongs to S. So we have a set of numbers. There is one c in that set and there are different numbers. If f at c is greater than all the f of x's in this set, all the f of x's, then it will be the maximum. If f of c is smaller than all the f of x's in this set, then it's going to be what we call exactly the absolute minimum value of f. These are what the definitions are. Both together, if I say find the absolute extrema of f, extrema comes from extreme values, all right? Then I will be asking for both absolute max and absolute min. Because when we say extrema, the extreme can be the extreme from the bottom, which is a minimum, or the extreme from the top, which is a maximum. So when we use the word extrema or extremum, then this means we are talking about either a max or a min. يعني هي الأطراف. So ممكن يكون عندنا max, ممكن يكون في min. Now this is what it means. My question is, let's look at some examples of functions to see what happens. Look at this basic function. It's defined for all real numbers. So the set S we're working with is from minus infinity to infinity. If you look, those two hands are continuing to plus infinity, right? This means no matter what value I take, something will always be bigger. Something will always be bigger. So can I find a biggest value for x from minus infinity to infinity? Compare the y values. What's happening to the y values? They are always increasing till they no end, till infinity. So this means there is no biggest value over all the set from minus infinity to infinity. So we say it has no absolute maximum. Whereas if we look at a minimum, we will notice that f of c here is less than or equal to all the function values. There is nothing less than f of c. So the smallest value you have is f of c. So what do we call f of c? The absolute minimum. Look at this upside down parabola. It has the other way around story. So if you look, it has no absolute minimum because the function keeps on going down to minus infinity. So whatever f value you take, there will always be smaller and smaller and smaller. So there's no smallest number or absolute minimum. But here f of c is greater than or equal to all the function values which come below it. So we say f at c is the absolute maximum value, or c comma f of c is the absolute maximum point. All right. So now let's look at a function and let's study it to see what happens when we change the set S. Let's look at the function y equals x squared minus 9. What is y equals x squared minus 9? It's a parabola shifted 9 units down. So if this is 3 units, this is 9 units down. It will be like this, where it cuts the x-axis. Where does it cut the x-axis? It cuts the x-axis when y equals 0, so x equals plus and minus 3. Right? This is how the curve looks like. From minus infinity to infinity, can I say what are the absolute max and what are the absolute minimum values? I say no absolute max, but there is an absolute minimum. What is the absolute minimum? It's this point over here. We all know that the vertex of a parabola will either be the absolute minimum or the absolute maximum of the function, because parabolas either look like this or upside down. If they look like this, this is the minimum. If they look upside down, then the vertex will be the maximum. This we call it the vertex, remember? And we can calculate for any parabola, just as a reminder for you. The vertex is calculated as, who can remember? Actually, it was on the top of my mind. I just know. Minus b over a, if I'm not mistaken. But you know when you get brain freeze. Minus b over 2a or minus b over a. minus b over 2a. Exactly. So it has x value equals minus b over 2a, and y you just calculated by putting this in the equation. So over here, how do we calculate a? This is ax squared plus bx plus c. So here a is 1, b is 0. All right, so that's why, what is the vertex? At 0, because minus 0 over 1 is 0. Y is 0 minus 9 minus 9. So whether we have the graph or not, we know where the vertex is. And we know since a is positive, then the parabola is up like this, a smiley parabola. So the vertex is the absolute minimum. So what do we have here as an absolute minimum of the function? Point. If I say point, I have to put the x and y value. If I say absolute minimum value, of course, the x can never be the absolute minimum value. The x is the location. The y is what we are comparing. It's y equals minus 9. Located at x equals 0. So this is part A. It's simple. Let's look at another example. The same example, but now I will change a little bit the domain I'm working on. I no longer want y equals x squared minus 9 over all its domain. I want to define this function only over the interval minus 3, 3 open. What will change in the function? It will look like open here at minus 3 and 3 where it used to cut. And it's still minus 3, minus 3, minus 9. Okay. Again, what does the absolute minimum point look like? It's still the same, nothing changed. It's at 0 minus 9. My question is, does it have an absolute maximum? Many students come and say the absolute maximum is minus 3, 3. Yeah, but this is not included in the domain. The domain is the open minus 3, 3. So those are open circles. So many students say if this is not the maximum, then the very next point close to it is the maximum. Come on. Is there any in math? Is there any point that is the closest to another point? No, because every single time I take a point, the midpoint is even closer. Take a point. Assume this is you saying is the closest. Then if you zoom in, the midpoint between this and minus 3 will be even closer, and so on, so like. So that's why it's very important to know that when we have open circles like this, then there is no next point to be a maximum. So again, what is our result? No absolute max. Because one of the first things that we said when we define is that the C that we are studying has to be in the set. So here, what is the maximum value of this function? The maximum y value of this function is 0. But f at minus 3 and f at 3, which give me 0 supposedly, are not included in the set I'm working with. So we have no absolute maximum point. Look what changes if we take the same function on this. What will happen when it's from minus 3 to 3? See, those two circles will close because they are included. So it will look like this. This is the curve that we're looking at now, only from minus 3 to 3. This still has the same absolute minimum point at 0 minus 9. But now, does it have an absolute maximum point? It has two absolute maximum points. What are they? Minus 3 y equals 0 and 3, 0. You tell me, is it allowed to have absolute maximum 2 points? Yes. When do we have two absolute maximum? When their function value is the same. We cannot have two absolute maximum points whose function value is not the same. But here, because what is the highest value in all the function? Highest y value. See, if I imagine a line going all the way to check where do I have the highest y value, when I reach here, I notice that I have the highest y value. What is my highest y value? 0. Where does this highest y value occur? It occurs 2 times, one at x equals -3 and one at x equals 3. That's why, how many absolute maximum value can we have? Only one. What's the absolute maximum value? 0. But where is it located? It's located at 2 places, at x equals plus and minus 3. This is why it's important to realize the difference between maximum value, maximum point, and the location of the maximum value or the maximum point. Now, this being said, it becomes now a question. Look at this. Look at this function. Because let me show you, it shows you different cases. So we want to try to find a pattern to know how to find absolute max and absolute min, because sometimes we cannot draw all the graphs. So we want to find a pattern in how functions are behaving to see if we can generate a rule on how to find maximum or minimum. As we saw here, for the same function, one time we found a maximum, no max, minimum, no max, sorry, here a minimum, no max, minimum, no, we changed the interval. We now have an absolute min and an absolute max. So what was changing? So that things changed. The interval where we are defining the function. Look on this now. F of x equal 1 over x, and we want to define it from -3 to 0 and from 0 to 3. Anyhow, it's not defined at 0 because we cannot. What is this? This is the hyperbola. Hyperbolas at -3, it's -1 over 3. So -1, -1, هيدا, -3 is here. So this is at -3. This is the point. And as we approach 0 from the left, so we keep on going down, because at -2, it's -half. At -1, it is -1. هيدا half. And a -1, and it keeps going down. We all know how the hyperbola, as we approach 0 from the left, the function will go down to -infinity. Now from 0 to 3, at 3 again it's equal to 1 over 3. It's a closed circle. At 2 it's equal to half. At 1 it's equal to 1, and this will keep on going all the way up, because as we approach 0, the function will go all the way up to +infinity. We all know the normal hyperbola. What's different between the normal hyperbola and this is that here it stops at -3 and here it stops at 3. So it starts from -3, stops at 3. We do not continue from the left and the right. Does this have an absolute max or an absolute min? Let's search for it. Does it have an absolute maximum point? I need to scan in my eyes from bottom up and find the maximum value where the function does not grow above it. I can't find such functional value because as I grow up, this grows all the way up to +infinity. So no number will be the biggest. And even here, what happens to the y values here? The y values are growing without bound. That's the idea when we talked about limits. See, the limit of this is -infinity, which means it decreases without bound. It keeps on decreasing and decreasing and decreasing. And the limit as we approach 0 from the right is +infinity, which means the function increases without bound. It will never stop increasing. So no matter which value we reach, we will always reach higher. No matter which value we reach, we will always reach lower. So no absolute max, and obviously no absolute min. Wow. So students, notice now that the interval we are defining the function on has a lot to do with our maximum and minimum. Moreover, the continuity of the function also plays a role, because see, 1 over x was not continuous at 0. And because it was not continuous at 0 and it had a vertical asymptote, the function did not have a maximum or a minimum. All right, so this is how it goes. So it goes without bound. Now, one of the things they were able to prove, which is a very big theorem, it's called the extreme value theorem. What does the extreme value theorem do? It gives us the pattern I was telling you about to know whether we have an absolute max or min for sure. Because obviously things are not guaranteed. Some functions have both, some functions have none, some functions have one of them. So there isn't really a strict rule about it. There is one case though, we can guarantee we have a max and a min. In other cases, things are guaranteed, no. In this case, things are guaranteed. We know for sure an absolute max and an absolute min happens. In the other cases, we cannot guarantee anything. So that's what the extreme value theorem does. That's what I want you to understand. This extreme value theorem guarantees that if the rules and conditions of this theorem occur, it guarantees that there is for sure an absolute max, absolute min for the function when it satisfies the conditions. That's what the extreme value theorem does. Now, what does the extreme value theorem say? It says that if you are working with a function f continuous over the closed interval. So what are the two conditions? F is continuous and the interval we are working with is closed. Then F attains, يعني it reaches both an absolute max and an absolute min over the interval AB. So in cases where we have a continuous function over a closed interval, in such a scenario, we can be sure without graphing the graph, without knowing anything about the function, anything, even if the function is Chinese for us. We don't know it, we can't understand it. If the function is continuous and the interval it's defined on is closed, then for sure we have an absolute max and an absolute min. This is what the extreme value theorem says. So now look at this function. The same function we were working with, 1 over x. Define it over the interval from 1 to 3 only. Is this closed? Yes. Is this continuous? Many students come and say, no, it's not continuous because we cannot divide by 0. No. Is this continuous over this interval? The only discontinuity of 1 over x is x equals 0. 0 is not in this interval. That's why f of x is continuous over the interval from 1 to 3. Those are the two conditions for the mean value for the extreme value theorem to be valid. So now what can we say? We can say f of x has an absolute max and min over the interval from 1 to 3. Perfect. We guaranteed they have one. Oh, this is basic. I guarantee they have one. Okay, fine. What is my goal? My goal is not guaranteeing they have one. My goal is, after guaranteeing they have one, what do we need to do? We need to find them. So our main goal is to find those absolute max and absolute min. But at least if they tell me that the function does have an absolute max and an absolute min, I know how to search. What do you mean you know how to search? See, if a function is continuous, let's assume a function is continuous over a closed interval. So A, I will take one negative, one on the positive, because it doesn't matter, right? Even I can, no need to draw the y line. It can be positive, negative, whatever you want. If the interval it's defined on is closed and the function is continuous, then I will start with a closed circle for sure, because it's continuous over the closed interval. So we start with a closed circle. We will go up, down as much as we want, go up and down till we reach what? A closed circle at B. This is how it will look like. The form might vary. This is one option. It could join from A to B directly. It could go down and then up. It could have so many shapes. But the trick is it does not break because it's continuous. If it does not break, yeah, this means I will keep on going as much as I can up and down, as much as I can, maybe 100 times, but I reach here at A, here at B, and I stop. This means, where shall I look at my absolute max and min? What are the options? What are the options? Either those are your max and min, because this is where you stop and this is where you end. So these can be values where the function has a maximum, minimum. So one of the options are the endpoints of your closed interval. What else are options you see? When the function is going up, I can't have an absolute max. But when I stop going up and I start going down, this point over here can be my absolute max. So it's one of the options. This here, those cannot be options. Why? Because the function here is decreasing. So if I choose this value, it can never be la max wala min. Why? Because the values were above it and the values here are continuing to go below it. So it cannot be nor a max nor a min. But when we reach here, this one is smaller than all around it. So again, it can be an option for me to be the smallest one in the whole function. Again, all those values where the function is increasing cannot be max or min, because if you choose one, you will find below it and above it. So neither a max nor a min. Above it and below it, neither a max nor a min. But when you reach here, the top of the mountain, this gives you another option. Here, all of these do not give me options at all, because if you choose any one of them, you find above it, which means it's not a max. You find below it, which means it's not a min. This one, though, is an option. Why? Because it looks like it's smaller than all around it. So maybe if we zoom out, it will be the smallest in the whole function. So I call it as an option. What else is an option? Nothing else. All these are not options, because if you choose any of them, the neighbor here is below it, the neighbor here is above it. So it cannot be a max, so it cannot be a min. So what are my only options? Beautiful. This helps me a lot. When I think of finding something in a function, I think of infinitely many numbers. But when I am able to settle my options into 6 options only, wow, that's a very, very good result. How do I know now which one of these options is my absolute max or min? Because I'm sure there is one. Because I'm sure I know one of these options has to be the max, one of them has to be the min. What do? I form a table with all these values I got. All the values I got, all my options. And I put them in the function. Then I find f of a, f at b, f at c, f at d, f at e, f at f. F at a, let's assume here I put values. A is 1 here. F at C is 2. F at D is -2. F at E is 5. F at F is -6. And F at B is 0. Which one is the highest number? This is the highest number, so this has to be my absolute max. Which one is the lowest number? -6. This has to be my absolute min. Is it true? Yes, obviously this is the max, because if I look from bottom up, this one is the highest value you can reach, and this one is the lowest value we did reach. So when the extreme value theorem works, so as a summary for you to now have the technique of solving, as a summary, if f is continuous over a closed interval AB, then f has an absolute max for sure. This is for sure, it has them, and min. Where to find them? Find them at, what options do you have? First, the endpoints. Second, what kind of points are these? So the options were the endpoints, one endpoint, second endpoint. And the other options were those points over here. What are those points? Those points are turning points. Turning points. What is special about turning points? We need to link derivative. This all are applications of derivatives, right? So if we have an application of derivatives, then I need to start thinking, how can derivative help me in this? Do those points have special derivatives? Oh, let me go back to the basics. Derivatives are what? By definition, they are slopes of tangents. Let me check, how do tangents here look like? Tangents for turning points are, can tell me, what do tangents at turning points look like? Brilliant. Tangents at turning points are horizontal tangents. Tangents at turning points are horizontal tangents. What is special about horizontal lines? Who can tell me what's special about horizontal lines? Horizontal lines have slopes equal to 0. That's one. That's one option. And I missed one of the options, one of the other options that the curve might have, and I think this will ring a bell. So the function I drew was a smooth function. Look at this function now. Between A, at A it's here, at B it's here. It can be like this. What kind of point is this? Look at this function. Is it continuous between A and B? Yes. Is it defined at all values between A and B? Yes. Where is the absolute max and absolute min? At this point and at this point. Right? So the options we look at, of course, these are not options at all, because these are between values that are smaller and bigger. So they are not options. What are the options for max and min? A, B, and C, and D. D is a turning point. What happens at turning points? The slope of the tangent is 0, which means the derivative, of course, is 0, because slopes of tangents are by definition. So here we have a horizontal tangent, which means its slope is equal to 0, which means the derivative is equal to 0. This point is also an option for max and min. But what happens at this point? We don't have a horizontal tangent here. What happens here? for this to have its shape, what kind of thing is this? This is a cusp. Remember cusps and corners? So to have a maximum, it should look like this. Either it turns like this, or it turns like this, or it turns straight like a corner. If to have a minimum, either it's smooth, or it's a cusp, or again it's a corner. For smooth ones, the tangent is horizontal, so the slope which is equal to the derivative are equal to 0. For cusps and corners, do you remember what those have? Those have derivatives that do not exist. Remember in the study of differentiability, what did we say about functions? When are they not differentiable? We said they are not differentiable when they are not continuous. We said they are not differentiable when we have corners and cusps like this. And they are not differentiable when they have a vertical tangent, which is not a case we are studying now. So when we have corners and cusps, which means the derivative does not exist, it's also one out of our options. So that's why, if I want to summarize now, if f is continuous over a closed interval, then we know for sure f has an absolute max and min. Where can those absolute max and min happen? They can happen at the endpoints. They can happen at points where the derivative is 0 or the derivative does not exist. Those points where the slope or the tangent or the derivative is 0 or the derivative does not exist are points which we call critical points. So now, as a statement, what are my options? As a summary, options are endpoints of the interval AB and critical points which belong to AB. What do students usually do? They find critical points. They don't test if they are in the interval. When I'm in the interval, everything has to be in the interval, or else it will be useless, right? So I only look for critical points, which means I find y prime equals 0 and solve for it. Y prime does not exist and solve for it. Very cool, right? So look at this. When can we have, what shapes can be max and min? Of course, the shapes that are smoothly, they are turns, or they are cusps and corners, which means the derivatives do not exist. So let me show you an example. Find the absolute extreme values of the function this is a polynomial, so continuous over all real numbers. In particular, what interval am I worried about only? -2, 4. This is the interval, it is closed. Those together means the extreme value theorem works. Extreme value theorem works معناتها what do we have for sure? An absolute max and an absolute min. Where do I search for them? What are my options? I search for them first when at endpoints. Second, I'll make here a box on the side. I need the derivative, which is 6x squared minus 6x minus 12, which is 6x squared minus x minus 12, which is 6x minus 4x plus 3. So x equals either -3 or x equals 4. So for f prime to be 0, critical points. So those are the endpoints. Now I want the critical points. How many critical points do I have? Two kinds of critical points. Derivative is 0. It gave me 2 critical points. I check, are those critical points in my interval? 4 is in the interval and it's already counted. -3 is less than -2, so this is rejected. I do not take it into consideration because it's not part of my interval. So did I make the correct? 6x squared minus 6x minus 12. Oh, I took 6 common factors, so it's -2. Sorry. So it's x minus 2, x plus 1. This changes things. Sorry for the mistake. So now x equals to 2 and x equals -1. Both -1 and 2, both of them are in my interval. So perfect. How many critical points do I have? 2. The second thing I look at is y prime does not exist. Common mistake. Students forget it. Do not forget this. Common mistakes that students forget it. So those are my options. How do I know which one has the absolute max value, who has the absolute min? Since those are only my options, then if I substitute the y value for each one of them, at -2, you put 2 times -2 cubed -8, so -16. -16 minus 12 minus 28. -28 plus 24, so 1. At 4, you get 37. At -1, you get 12. At 2, you get -15. So the options you have to only study for absolute max and absolute min gave me those values. So this means this is the biggest value. Here happens the absolute max. This is the smallest value. Here happens the absolute min. So I can say the absolute maximum value is y equals 37. I want to make, so the absolute maximum value is y equals 37 located at x equals 4, and the absolute minimum value is y equals -15 located at x equals 2. The absolute maximum and minimum points are 437 and 2 minus 15. This is if you want to just understand the mathematical language that we use. Let me give you another example. Given the function y equals 4x5 to the power 5 over 4 over 0 to 4. You tell me, how do I know where these functions, if the function is continuous or not? These are power functions. في fourth root. So if you want to think about them on the side, what does x to the power 5 over 4 mean? It means it's x to the power 5 under the fourth root, and this is x under the fourth root. Even roots are only defined when the value inside of them is positive. What is the interval we're using? From 0 to 4. So it's positive, right? So they are defined and continuous, because when I get the domain of definition, so the domain of definition of this function is x has to be greater than or equal to 0. What do we have here? Perfect, because what are we working with? 0 to 4. So continuous is guaranteed now that we know the domain of definition and we know this function is continuous over its domain, plus the interval is closed. So by the EVT, we for sure have what? An absolute max and absolute min. Where do I look for those absolute max and absolute min? I look at endpoints, which are 0 and 4. Second, I need critical points. Critical points, what does that mean? Critical points depend on derivative. So the first step is find the derivative and simplify it, because then what do we do after finding the derivative? We need to find zeros and undefined values. Remember this discussion when I told you you have to simplify your derivative, because later on you will be finding zeros of the derivative. Ta-da! This is one of the cases. So y prime is what? 4 times 5 over 4, 5. X to the power 5 over 4 minus 1, 1 over 4. Minus 8 times 1 over 4, 2. X to the power 1 over 4 minus 1 is minus 3 over 4. I have taught you this before, that the first thing you have to do is bring the power that is negative down. And I also told you when we have roots, take a common denominator, because this simplifies a lot. Because always those two will simplify, because here you need to multiply 5x to the power 1 over 4. I will write it in 2 steps so you can get the chance to see what happened. Minus 2. But what is 5x times x to the power 3 over 4? You end up adding the power. 1 over 4 plus 3 over 4 is 4 over 4. 4 over 4 is 1. So it's 5x minus 2. Simply imagine all this complicated problem. Its derivative is this function. This makes, when I simplify as such, it makes it easier to answer my questions. My first question is, when is y prime equal to 0? A function is equal to 0, a fraction is equal to 0, when the numerator is 0. So when 5x minus 2 is 0, this means 5x equals to 2, so x equals 2 over 5. When is it not defined? When does the derivative not exist? This derivative exists everywhere except when x to the power 3 over 4 is 0. Yani x is equal to 0. So how many critical numbers do we have? 2 numbers. You tell me this, the function is not defined, so it's not part of the domain. No, this is part of the domain. It's not part of the domain of the derivative. So the derivative is not defined here, not the function. The function is defined at 0. What is the function at 0? 4 times 0 minus 8 times 0, it's 0, 0. So is the function defined at 0? Yes. So this means when I say it does not exist, what did I mean? I mean the derivative does not exist. If the derivative does not exist, this means that the point can be a cusp or a corner, or the point can be a place where I have a vertical tangent. But that's the idea. It's not anything else. So now I ask myself, is 0 in the domain? Because what is the domain I'm working with? From 0 to 4. Yes, and it's already registered. So that's why I write it. But I don't really need to write it. It's a critical point, but it's already here in my table. What's the second critical point? 2 over 5. Is it between 0 and 4? Yes. Now what do I do to know where is the absolute max, where is the absolute min? 0 when substituted here, the answer is 0. 4 when substituted here, I will calculate it. 4 multiplied by 4 to the power 5 over 4 minus 8 4 to the power 1 11.3 something. If you want it in exact form, just to go back to some algebra, it's 4 raised to the power 5 over 4 minus 8 4 raised to the power 1 over 4. This is 4 raised to the power 5. It's 2 to the power 2. So it's 2 to the power 10 over 4 minus 8. 2 to the power 2 over 4, which is half. So this is 5 over 2. 4 times 4 root 2 minus 8 root 2. So it's 8 root 2, the answer, if you want in exact form. Practice this. This is a lot of simplification of powers. 8 root 2. The calculator, if you are lucky, will give you 8√2. In my case, it gave me, because my calculator is a bit old, it gave me 11.3. So it's an approximation. At 2/5, what do we get? At 2/5, so I will go back to the calculator. 2/5, change it. You get minus 5.1. So what do we notice? We notice here we have an absolute max. Here we have an absolute min. So you can make this conclusion. Absolute maximum value of 11.3 at x equals 4. Absolute minimum value of minus 5.1 at x equals 2/5. So it's nice. Look at this example. One more example on this. Function f of x equals x cubed minus 5x plus 3 sine x squared. Oh, this no. So it's good I reached this problem, because example number 3.13, you do not need to solve this. You tell me why I do not need to solve it. Because the derivative will look like this. See, it has x and sine and so on. The derivative will look like x and cosine. You will have to put it equal to 0 and solve it. Do you know how to solve this? Equal to 0? No. It needs numerical analysis, and we don't learn numerical analysis in our course. So problems that have these are not going to be included. Problems like this, because you cannot find zeros. The idea is, the main idea in problems like these is finding zeros of the derivative and undefined values of the derivative. If I can't find zeros of the derivative, then what added value is it? For me, at least now, because we don't have the tools. All right? So be very careful about that. Because those are not included. So this is basically all my talk about absolute max and absolute min. What will I do next? I will do local max and local